Module 9, Protein Needs for Muscle Hypertrophy. Protein has been well known throughout the centuries as a very, very important part of the human body as far as macronutrient need. And it goes back as far as the ancient Olympians who ate a huge amount of meat. In the 6th century BC, one of the most famous athletes was Milos, who was a wrestler who won 5 gold medals in the ancient Olympics. And he was reported to eat about 10 kilograms of beef every day just to support his training. The tradition, or anecdotally speaking, is with athletes to consume high protein intake because that's what you need for muscle hypertrophy. In fact, the average intake of bodybuilders and varsity level football players averages about 3 to 4 grams per kilogram of body mass per day. That's a pretty substantial amount. It's not uncommon to see athletes, particularly football players, to ingest 80 egg whites, 4 liters of milk, and 250 grams of protein powder per day because it's a traditional thing to do, and it's what most people think of when they think of building muscle. In actuality, if we look at resistance-trained athletes, and in this one particular study, which was nicely done in young males, there was no difference between consuming 2.6 grams per kilogram of day of protein versus 1.35 grams per kilogram per day. And in this study, any of the excess intake basically led to increased amino acid oxidation. So all those additional amino acids were simply being utilized for energy needs, and it didn't stimulate an increase overall in whole body protein synthesis. As far as endurance exercise is concerned, we actually see an increase in leucine oxidation. Remember, leucine is a branched chain amino acid, so that does increase. However, it is also going to attenuate muscle FSR, which stands for fractional synthetic rate, so the amount of production of protein in the muscle is actually reduced as a result of performing endurance exercise. So there's really no added benefit of excess protein, and the idea is really to just match body needs with an appropriate amount of intake in order to get optimal protein synthesis. So, to answer this question, are high intakes really necessary for optimal muscle hypertrophy? Not in the amounts that most athletes think of. So yes, people do need more protein intake when they are an athlete compared with non-athletes. However, it's not to the level that most people think they should be consuming it. And later on in this lecture, I'll show you a table of what's recommended as far as protein intake for various athletic populations. So let's first start our discussion of protein synthesis and degradation with what's called protein turnover. So what is protein turnover? Well, protein turnover is basically the amount of synthesis or production of protein versus the amount of degradation. And the whole idea for optimizing protein synthesis is really to remain in balance. So there needs to be some protein catabolism or breakdown, but we also, of course, want to have some protein synthesis. And it's interesting when you take a look at the amount of synthesized protein each day, about 200 out of the 300 grams that are produced in the human body are actually coming from recycled amino acids. So we do a really good job of recycling any amino acids that are hanging around that aren't being utilized for protein synthesis. And so we just recycle them. So how does diet affect protein turnover? Well, it seems that we should have adequate energy overall, as well as carbohydrate, to have a positive effect on protein balance. So if we consume carbohydrates, that's actually beneficial because we are releasing insulin, of course, when we consume carbohydrates, which stimulates protein synthesis. Remember that insulin is a building hormone. Insulin also will result in the inhibition of protein breakdown. So we'll break down less protein. Since we're producing more protein, we certainly don't want to have a lot of protein breakdown going on, because insulin, as I already said, is a storage hormone and it's a building hormone. We also can attenuate plasma and sweat urea excretion. So remember, urea is the amine group that's being deaminated from an amino acid that's no longer needed, and we're left with the carbon skeleton. And so we'll actually reduce the amount of urea excreted after an endurance exercise event, so we're wasting less. If we have amino acids in the diet, we will, of course, increase fractional synthetic rates. So we're going to have some protein building. We'll decrease FBR, or fractional breakdown rate, which will reduce the amount of protein degradation. So overall, we shift the entire paradigm of synthesis and degradation towards positive nitrogen balance, or positive protein synthesis, which is a good thing. So it behooves us to have both carbohydrate and protein in our diet in order to reap the benefits of protein synthesis. So one of the things that we want to try to do in all of these research studies is to assess protein status of an athlete somehow. So how can you do this? Well, first off, let's talk about what nitrogen balance is. Dietary protein contains about 16% nitrogen, and it's what's nitrogen that makes amino acids so special. That nitrogen, that amine group, is very, very important to us. It represents our only source of nitrogen. And so in order to meet our needs, we need to be consuming some sort of protein on a regular basis. So nitrogen balance is all about intake of nitrogen through protein, as well as how much do we lose through excretion. So nitrogen in is going to be our protein intake, or a dietary intake of protein, while our excretion of protein, or nitrogen, so protein losses, really can be excreted several different ways. The first of which is through the urea cycle. So the liver, remember, performs the urea cycle. It's deaminating the amino acids that are no longer necessary and taking that amine group that has the nitrogen in it and basically creating this substance urea, which then has to be thrown out into the bloodstream, and the kidneys will filter out the urea in urine. So thus we have losses of nitrogen through urine or urinary nitrogen. So about 86 to 90% is coming from urea. However, we do have other losses from creatinine, from overall ammonia, from uric acid, and some other nitrogen containing compounds. So there are a variety of mechanisms by which we can lose nitrogen through cellular metabolism. Now, we lose some nitrogen as well in feces. So any undigested proteins, the sloughing off of the gastrointestinal tract cells, we lose some protein as well there. The gut microflora can also produce some amino acids that we can lose. We can sweat some of the nitrogen out. We also have mechanical wear. So any sloughed off skin cells, fingernails, hair, blood, semen, all of these represent losses of nitrogen for us. So when we're in positive balance, that means we are going to be producing more lean tissue. So we have lean tissue synthesis. So we have training plus the appropriate amount of protein intake plus the adequate amount of kilocalories will push us into a positive nitrogen balance. That's a good thing for the athlete. Conversely, we can be in negative balance, where we're going to have lean tissue degradation, and this is going to cause decrements in performance for the athlete. So this is when we have hard training and couple that with low calorie intake. That spells negative nitrogen balance for the athlete, and perhaps again decreases in overall performance. So what we want to try to do is to match the loss of nitrogen with an equal amount of intake of nitrogen. And many decades ago, this was looked at quite closely, and they developed an equation through research to try and determine the loss of nitrogen and how much nitrogen to replace in someone's diet. And so what you would do is monitor the protein intake in grams per day and divide that by 6.25, and then subtract the urinary urea nitrogen in grams plus 4. So you do have to collect urine samples and fecal samples over a 24-hour period of time to determine how much nitrogen the person is losing. Thankfully, researchers have done this quite a bit and quite often and determined that the minimum amount of protein intake to match the loss of protein ends up being about 0.5 grams per kilogram of body mass per day if the person is consuming a high-quality protein. Now, what's a high-quality protein? Well, we'll define that a little bit later on in this lecture. As well as this minimum amount only applies to non-pregnant, non-lactating adults. So for women who are pregnant, who are lactating, there are different values for protein intake. So the DRI recommendation, which all of this is based on, ends up being 0.8 grams per kilogram of body mass per day for most adults. Now, how did they come up with this value? Well, they basically wanted to cover the bulk of the population, so they looked at the adolescent male, which has the highest amount of protein intake of all populations across the board. So 0.8 actually covers about 98% of the population as far as their protein needs are concerned. Of course, there are going to be some extenuating circumstances, and athletes certainly fall into this category. 0.8 grams per kilogram of body mass is a little bit low for the athletic population, as we'll talk about a little bit later. So how would you monitor the amount of nitrogen loss? Well, you can also use what's known as tracer methods, and basically what you're doing here is radio labeling an isotope like carbon-13 or carbon-14 or specific amino acids. Leucine is used quite a bit as a radio label tracer, and then you basically follow where these radioactive substances go in the human body. And from this is what we can infer as the fractional synthetic rate. So you can see how these amino acids or this radio label isotope is being incorporated into, for example, muscle tissue, and you see how much of it increases over a certain period of time, and that tells you how much nitrogen is being utilized. So you could also use 3-methylhistidine excretion or N-methylhistidine excretion. And this is basically histidine as amino acid with a methyl group attached to it, and gets incorporated into contractile proteins. And then what you can do is that as muscle protein is being degraded and this 3-methylhistidine is released, which can't be recycled, it actually gets excreted in urine. So you collect urine samples and measure the level of 3-methylhistidine excretion or concentration in the urine, and then that's used to basically come up with how much protein was broken down. The only problem is that you do have to take into account some other contractile proteins in the gut as well as the skin because that can confound your results. So as far as protein synthesis is concerned, how do we make proteins? How do we build proteins? Well, this comes down to two very, very important steps, and that is transcription and translation, as we'll talk about on the next slide here. For transcription, this is all about producing some kind of roadmap, some kind of architectural plan to build the protein that we're looking to build. So when we increase transcription, we are actually producing an architectural plan, or mRNA, to basically have directions on how to build a particular protein. And it's a very complicated process that I've outlined very rudimentary here. But the important point to come away with is this, and that is, in the DNA, we don't want to use the entire DNA strand or make an entire copy of the DNA strand to produce one given protein that we're trying to make. So if we're trying to make, actin or myosin, we don't want to have a copy of the entire DNA strand to make actin or myosin. We want to basically copy only the sequence of DNA that calls for those proteins. So think of it this way. The way I like to describe it is, if you were going on a road trip and you were going on a road trip to another city within your state, you wouldn't need a map of the United States in order to get you to that particular city. You would simply need a state map to get you to that city, or perhaps even a county map. So you would use a much smaller portion of the DNA. You would use a much smaller geographically located map in order to get you to that particular city, in order to make that particular protein. This, of course, assumes that you're not using a GPS to get you to where you need to go. So this diagram shows you the transcription process. So up here, the yellow blob that you see, that's the nucleus of a cell. And we have DNA, this blue strand here, that has unraveled so that we can produce a copy of the sequence of DNA that calls for whatever protein that we're trying to make in this instance. That mRNA, messenger RNA, is our state map. That's our architectural plan for building proteins, so that ends up going into the cytosol of the cell, and then the ribosome here, which is another protein, will come along and read this map to produce the protein that we're trying to make. That's where translation comes into play. So translation is basically translating our architectural plan or our state map and using that map to build the protein that we're trying to make. So this is where the ribosome, this is where the tRNA comes into place, and we put together amino acids in a very, very specific amino acid sequence so that we can make the protein that we want to try and make. So this slide is just showing you how translation, we have the ribosomes here, those white blobs with the tRNA bringing in or transporting the amino acids, which are represented by the different colored balls that you see attached to this squiggly tRNA thing. And so that they're bringing that along, and you're attaching amino acids as you're reading, as the ribosome is reading the architectural plan or that state map. And so eventually then you end up with this really long protein that can be turned into whatever protein, if it's globular in nature or linear, etc., to perform the job that you need it to perform. So that's protein synthesis in a nutshell. So what about the effect of exercise on protein synthesis? Exercise is the greatest potent physiological stress that we can put on our bodies to force protein synthesis to happen. Why? Because this is an adaptive response of the cell in order to overcome, with training and over time, the need for protein. So overall, exercise is going to increase protein synthesis. If you exercise, you will increase protein synthesis. That's the bottom line. There is a difference between endurance exercise and resistance exercise. It turns out that there are far more mRNA species expressed with endurance exercise than with resistance exercise. So there is a difference phenotypically in what we'll see with the different and variety of endurance exercise activities. The intensity is, as far as muscle hypertrophy is concerned, really is the key to forcing protein synthesis and to get muscle hypertrophy to occur. So the intensity just refers to the amplitude of mechanical stress that we're placing on the human body as a result of lifting these heavy objects, these weights that we're trying to force our muscles to move in various manners. So what happens? How does muscle hypertrophy happen? Well, basically we have these forceful contractions. So you're doing the weight training, you're performing them at a high intensity, and that ends up causing sarcolemmal wounding. Now, if you remember, the sarcolemmal membrane is what surrounds the muscle fibers, where all the sarcomeres are located, all the actin and myosin filaments. Now, that sarcolemmal membrane has to remain intact. If it does not remain intact, what ends up happening is that you burst the membrane, and then calcium leaches in, which then will cause, as we'll talk about just a little bit later, the breakdown of muscle protein via the calcium-activated calpain mechanism. So we want to be careful and, yes, provide forceful contractions that are intense, but that old adage of no pain, no gain should really be avoided when it comes to trying to get muscle hypertrophy. That sarcolemmal membrane has to remain intact. It needs to be stressed. We'll wound it a little bit, quote unquote, which then causes the release of growth factors. These growth factors include insulin-like growth factor 1, as well as fibroblast growth factor, which cause the release of satellite cell activation. Satellite cells are used to add more protein to the existing sarcomeres, and then that's going to also increase protein synthesis. So we've got the cells as a foundation, these satellite cells that will provide the foundation for new sarcomeres that are added, and then we're also going to transport more amino acids in and have this increase in protein synthesis so that we build more muscle. Now, the duration of exercise also makes a difference as far as muscle hypertrophy is concerned. Typically, the longer duration activities like marathons, ultra endurance events, these are less likely to cause an enhancement in protein synthesis. Training status also makes a difference. So whether or not you're well trained or whether you're beginning, this is also going to affect the rate at which we see protein synthesis occur. So now let's take a look at a few different scenarios here. Short-term exercise, acute resistance exercise, and also long-term. In the short term, as far as a potent physiological effect is concerned, we see an increase within 4 hours of exercise of protein synthesis. However, there's no change in total RNA. So although that you see this protein synthesis increasing, you may not necessarily get an increase in all of the messenger RNA to code for more proteins. There is an increase again in protein synthesis, but a change in myosin mRNA may not necessarily happen with short-term types of exercise. So perhaps there's something post-translationally. So after we have performed transcription and translation, that still remains to be elucidated. So what about acute resistance exercise? Well, overall, there's no change in whole body protein synthesis during and up to several hours after the bout of resistance exercise. However, we do see an increase in fractional synthetic rate anywhere from 36 to 48 hours post-resistance exercise in both men and women. The really exciting thing, too, is that this also can happen in the elderly, which means that the elderly can also have a positive benefit from weight training. Now, well-trained athletes will overall have greater whole body protein synthesis versus somebody who's sedentary, simply because they do have a larger muscle mass that they have to maintain. In the long term with exercise, we see an increase in myosin mRNA expression, so perhaps there's something pre-translationally that may be going on here as well. We're still not quite sure. The bottom line here is that we definitely need more studies warranted and looking at the amino acids and how specific amino acids are contributing to the process of protein synthesis. So now let's take a look at the protein degradation side of things and our contributions of intracellular free amino acid and contribution to that amino acid pool that we saw earlier in the course. So this diagram outlines very simply the shifting of amino acids between the liver. So this here is the liver. And we also have muscle here on the right-hand side of the diagram. And basically, if we start at the top here with the ingestion of dietary protein, of course, we have to digest that protein, absorb it, transport it, and shift it out to the bloodstream, which contributes to the amino acid pool. That amino acid pool then can be drawn from by muscle tissue and get intracellular amino acids, where we have synthesis going on for protein, as well as degradation contributing back to the intracellular amino acid pool. Now, that amino acid pool can also be drawn from by the liver. And so the liver can take these amino acids in to have an intracellular amino acid pool. We can, of course, have synthesis of protein as well as degradation of protein to release those amino acids. Now, we can use those intracellular amino acids in the liver to produce specialized products like the visceral proteins that we mentioned early on. Or we can simply deaminate those amino acids and be left with a carbon skeleton and get rid of that nitrogen or that amino group via urea and the urine. So that's the process of protein degradation. There are three basic pathways for the breakdown of protein within muscle. The first of which is the lysosomal pathway, which occurs when basically you have a significant amount of muscle damage occurring within the muscle. So you try the no pain, no gain philosophy. That's going to result in major inflammation, and the lysosomes are going to be mobilized to degrade that muscle fiber or muscle fibers to basically remove those fibers and get rid of all the damage. And we also have the non-lysosomal pathways, which are calcium-activated calpain pathways. This is a neutral protease that basically is thought to play a role in proteolysis during exercise. So you're utilizing some amino acids for energy production via this pathway. But overall, it's not destructive to the muscle tissue. Then there's the non-lysosomal pathway, which is ATP dependent and requires ubiquitin. This is activated during times where the human body may be in a mode of starvation or when there's sedentary, so there's disuse of the muscle and muscle atrophies. These pathways will be activated. As far as protein catabolism after an acute endurance exercise event, we know that during this type of event, we use about 1 to 6% of amino acids at 65% of VO2 peak for ATP production. We end up with higher plasma urea concentrations. We also sweat out more urea and, of course, urinate more urea out. If you compound that problem with a hot and humid environment, then you're going to get even more so from there. You'll also, as far as rates of oxidation in specific amino acids, research has shown that leucine and lysine tend to be more highly oxidized. This does return back to baseline levels once you stop exercising. However, the leucine and lysine oxidation can persist for a while as far as being amino acids that are utilized for ATP production. And we know that the intake of carbohydrates during this period of time can actually attenuate this whole process. So an acute endurance exercise event will have these effects on protein catabolism. If we extend that out to chronic endurance training, at rest, whole body protein synthesis is actually increased, so that's a step in the right direction. Nitrogen balance does become less negative, so the intake is offset by some of the losses, or perhaps some of the loss is less, and intake may remain the same. There is less leucine oxidation for the contribution of ATP production, and it's going to be less with individuals who are trained compared with sedentary people. You take sedentary people and put them on a chronic endurance training program, they're going to have higher amounts of leucine oxidation. You'll also get less branched chain oxoacid dehydrogenase activation. So again, you're going to be using less of the branched chain amino acids, so that leucine, isoleucine, and lysine are all going to be less as far as their utilization for ATP production is concerned. So you'll get amino acid oxidation sparing with training. As far as resistance exercise is concerned, if you look at just an acute bout of resistance exercise, as far as protein catabolism is concerned, we don't see a change in leucine oxidation. However, the FBR, the fractional protein breakdown rate, is actually increased. But when you take a look at the fractional synthetic rate, it actually increases more so you still remain in a positive nitrogen balance. In a fasted state, of course, net protein balance is going to be negative, and what's interesting is that acute resistance exercise actually makes that net balance a little bit less negative as far as the nitrogen is concerned. And eating is going to be, the timing of eating that is very significant as far as post-exercise is concerned. So that makes a difference when we're talking about fasted state and a fed state as far as a bout of acute resistance exercise is concerned. We also get an increase in plasma testosterone levels, which again promotes protein synthesis. As far as chronic resistance training, so we continue to be on our training program. What happens here? Well, at the onset of a training program, so if you just begin a training program, you will get a negative nitrogen balance. However, as you continue your training program, eventually this is going to return back to baseline values. That happens in about 20 days, according to some of the literature. So you'll get an increase in the fractional synthetic rate with training, and whole body turnover as far as protein is going to be much greater in individuals who actually train on a regular basis compared with sedentary folks. So you're headed more towards a positive nitrogen balance and more protein synthesis than you are degradation. There are some gender differences as far as protein catabolism is concerned. Men tend to utilize more carbohydrate and protein during exercise compared with women. So if we shift gears a little bit and talk about how we regulate protein catabolism and protein synthesis, there are some hormones involved. And as we have seen a few times previous to this, insulin is a hormone that does regulate macronutrient distribution, and there's no exception here for protein. Insulin is, remember, a protein storage hormone. It's a building hormone. It's going to promote protein synthesis. So with insulin and promoting the release of insulin, we get less proteolysis of muscle, so there's less protein catabolism. You're going to have more protein synthesis, especially when there's lots of amino acids available. You'll increase the fractional synthetic rate and, of course, increase amino acid transport to muscle tissue as long as there's a nice pool of amino acids available. At rest, you tend to have much more of a positive protein balance and increased protein synthesis, and as well as an increase in amino acid transport. And if we're looking at post-resistance exercise, doesn't seem to have an effect on synthesis. However, you get a reduction in the amount of degradation that you'll get from insulin release. But the good news is that you're going to increase the amount of amino acid transport to help with making sure that there's this constant flow of amino acids to muscle tissue. So insulin has a very, very positive effect on protein anabolism or protein synthesis. Now, cortisol is another hormone, which is a stress hormone or a breakdown hormone. It's secreted from the adrenal cortex, and it will increase protein catabolism, especially in response to things like stress. And exercise is a kind of stress, which, of course, is going to promote protein catabolism, as we have seen in some of the previous slides here. It's going to allow for more glucogenic amino acids to be available. So you're going to be taking these amino acids that are glucogenic and turning them into glucose. So this increases gluconeogenesis. And remember, gluconeogenesis is production of new glucose from non-carbohydrate sources, i.e. amino acids here. It does inhibit glucose uptake by muscle, so the muscle isn't going to get as much glucose with cortisol release and higher levels of cortisol release. You're going to stimulate lipolysis, so you're going to stimulate the breakdown of triglycerides from adipose tissue. You're going to inhibit growth and inhibit growth hormone release. So this all works against the idea of muscle hypertrophy. Testosterone is going to increase lean body mass. And the neat thing about testosterone is that you can inject yourself with this stuff and you get increases in muscle mass without having to do anything. Now, of course, we're not recommending that athletes inject themselves with steroids, but from some of the research in laboratory animals and, of course, some studies looking at survey studies of humans who have consumed testosterone, we know that we can get increases in lean body mass. So this is going to promote protein synthesis. You're going to get more intramuscular reutilization of amino acids, and you're not going to affect protein degradation very much. With growth hormone, or somatotropin, this is released from the anterior pituitary gland, and it does increase dietary protein, it's increased by dietary protein. And so ingestion of dietary protein will promote growth hormone release. It's also increased with exercise on a temporary basis, I think for about 24 to 72 hours, somewhere in that time frame. And you'll get more increases in growth hormone with anaerobic or non-oxidative work versus aerobic activities. So we can naturally enhance growth hormone simply by doing very, very high intense short bouts of exercise. This does shift energy away from adipose tissue to lean body mass, so it's increasing the availability of fatty acids so that we can utilize them for energy purposes, and it also increases the release of IGF-1, or insulin-like glucagon factor 1 from the liver, which is going to increase protein synthesis and deliver more amino acids to the muscle. So as far as overall growth hormone increasing protein synthesis, we do need a little bit more work in that area. So that's just preliminary as of this recording. Insulin-like growth factor, or IGF-1, is also known as somatomedin C. It is released locally with exercise or with growth hormone, as we saw. It's going to increase the uptake of amino acid into muscle cells, so you're going to get more protein synthesis as well. And you'll get a stimulation of muscle hypertrophy and differentiation of cells so that they become the myofibrils. So this promotes muscle hypertrophy, and if you also think about the material that we talked about earlier, where to get muscle hypertrophy to occur, we have to have sarcolemmal wounding so that you do release growth factors like IGF-1 as well as fibroblast growth factor. So shifting gears a little bit here, let's talk about protein quality. You'll often hear, particularly bodybuilders, talking about protein quality. So what is protein quality? Well, protein quality just refers to whether or not that particular protein has all of the essential amino acids. It has extra amino acids for the synthesis as well of non-essential amino acids. So you got all these essential amino acids plus a little extra so that you then can make the non-essential amino acids. It's also going to have good digestibility. So plant sources of protein, you get pretty decent digestibility. 70 to 90% of what you ingest will actually be absorbed. As far as animal sources, it improves a little bit more to 90 to 95%. So it's much easier to get a higher quality protein from an animal source than it is a plant source. However, it's not impossible to get all of your high quality proteins from plant sources. So what's the difference between an incomplete protein and a complete protein? Well, an incomplete protein might have all of the essential amino acids, but they may be low in one or two. They may be, limited as far as how much contribution of that particular amino acid to the total needed by the human body. Now, you could have some proteins that are incomplete proteins that don't have all the essential amino acids as well. This doesn't mean that they're bad proteins or that you can't eat these proteins. It just means that you require other sources of proteins to kind of fill in the gaps a little bit. So as an example here, soy protein is actually considered a complete protein. It's got all the essential amino acids and a little extra. However, if you're looking at plants in general, there are some amino acids that do limit the use of plant proteins as a complete protein. So the four most common limiting amino acids are listed here. So lysine, methionine, threonine, and tryptophan, which are found in the food sources listed here below. Those are limiting because they are not found in large quantities in these foods and could represent an area where somebody needs to be a little bit more cognizant about how am I going to get my complete protein. So again, to reiterate, an incomplete protein doesn't necessarily mean that it's inadequate or completely useless. It just means that you've got to combine food sources to get that complete protein and to meet all the needs for essential amino acids in the human body. So how do we use this idea of combining proteins that may be incomplete or limiting in a particular amino acids? Well, we use something called complementary proteins so that you can get a complete protein. So this table is an example of what you could do here. So basically what you do is combine foods from 2 or more of these categories and you get a complete protein. So for example, maybe you have some pasta and then you have some dried peas or dried lentils that you've incorporated into that pasta. That then, when you combine those 2 products, makes a complete protein, whereas individually they would be incomplete and thus limiting as far as the amino acids, essential amino acids that you would be getting. So just as another example, you could combine, for example, some sesame seeds with some leafy greens, maybe in a salad or something like that. That would make a complete protein. So here are some other examples. Stir-fried vegetables and tofu over rice, vegetable chili with cornbread, oatmeal with nuts and soy milk, spinach salad with vegetables, garbanzo beans, and sunflower seeds. When you combine those foods together, you get a complete protein. So it's got all the essential amino acids, and you don't have to worry about any deficits happening in the diet, assuming that the person is consuming a regularly balanced diet on a regular basis. So how do I determine protein quality of food? Well, on a very simplistic manner, you could look at what's called the amino acid score or the chemical score. And what's used as the standard here is the egg. That's the ideal protein as the reference food. So it gets a score of 100%. And essentially, this is just looking at the number of milligrams of essential amino acids in 1 gram of the reference or the test protein over milligrams of essential amino acids and 1 gram of a reference protein. So you're looking at how many essential amino acids are actually in the food that you're trying to determine what the amino acid score is. The problem with this method is that it doesn't measure the digestibility of the protein. So remember, there are differences between plant sources and animal sources, and that needs to be taken into account as well. So you can't just look at what amino acids are in a particular food and then use that as your measure for protein quality, although early on this was the method that was used. So here's a table showing you the amino acid rating of some foods here. And I've got soybeans as a reference because that's a pretty popular protein source for a lot of people, especially vegetarians and vegans. And soybeans, when you look at just the amino acid score, it gets a score of 47 out of 100. So it doesn't get a very high score as far as protein quality is concerned. And if you just keep this in mind as we go to the next protein quality measure, I think it'll be a nice example to show how the amino acid score really doesn't give you a complete picture. So what does give us a better picture, it's not a perfect picture, but it's a better picture, is what's called the protein digestibility corrected for amino acid score, the PDCAAS. And this is what the FDA uses as their measure of protein quality. And basically it does take into account digestibility of the proteins. So what they try to do is reflect it as part of the percent daily value. So how much you're getting of that particular nutrient out of your necessary daily value that you're supposed to be getting. So the equation for this is percent daily value equals the serving size in grams multiplied by the PDCAAS, divide that by 50. So if you took, for example, pinto beans here, the serving size is 7 grams per half a cup as far as the amount of protein that you're getting. You look at the PDCAAS value for this, that's 0.66. So you would take 7 grams times 0.66 divided by 50, and you come up with a 9% daily value. So if you consume a half a cup of pinto beans, you would get about 9% of your daily value for protein. So this, as I mentioned, the PDCAAS is a measure of protein quality that is looking at the amino acid composition relative to the amino acids necessary for a 2 to 5 year old child and adjusting that for digestibility. So that's the big key here is digestibility. So the higher the score, the less for that particular protein that you're going to need to get all of your amino acids. So this table here shows you the PDC AAS of a variety of foods. And if you recall, I asked you to remember the soybean value. And if we look down the list here, we've got isolated soybean protein and soybean protein concentrate. And the difference there is just a little bit of a protein. It depends on how you extract the protein from a soybean. And that's going to dictate whether it's a concentrate or an isolated soybean protein. But anyhow, they get a score of about 100%. And just as in the amino acid score, they score just about perfect with egg whites here. So egg whites, the gold standard, and soybean proteins in the concentrate and the isolated form seem to be a pretty good as far as this is concerned in these data. As far as getting amino acids and essential amino acids and using this as a protein source, high quality protein source, a complete protein source. We move on to the protein efficiency ratio, which tries to look at protein quality from a different perspective and looking at basically how these amino acids can promote growth in animals. So protein efficiency ratio is looking at the ingestion of protein and looking at how well an animal develops. And basically this is used more so than not in infant formula in determining whether or not the protein constituents in supplement formula is appropriate for promoting growth in infants. And the equation for this is basically your body mass gain when fed a test protein versus the body mass gain when fed a reference protein. Now we can use the net protein utilization, and this is looking at it again from a slightly different perspective, and that is how do we incorporate the protein and use it for body growth and maintenance of tissue. So this is really looking at nitrogen and the amount of nitrogen we retain versus the amount of nitrogen intake, and then multiplying that by 100 to see what the actual utilization of the protein was. So the higher quality the protein, theoretically you should get more retention of that nitrogen and more utilization of that nitrogen. Then there's the biological value, which is again using the protein as a way of looking at how do we support growth, how do we maintain body tissues. And this equation is very similar, and it's looking at nitrogen retained versus nitrogen absorbed, and then multiplying that by 100. So an egg would get, again, a perfect score of 100, whereas corn would get a score of 60. So how much protein do athletes actually need? Well, there are some considerations here that we need to look at first. And the first of which is the total kcal needs for a particular athlete given the amount of work that they actually do. So as far as a percentage of total kilocalories protein-wise, you need about 12 to 20% for most athletes as far as total kilocalories are concerned. There needs to be some carbohydrate, so depending upon the carbohydrate availability, if someone's on a lower carbohydrate diet, obviously we have to fill the need for calories some other way, so it's either going to come from fat or protein or a combination of the two. The amount that the person exercises as far as exercise intensity is concerned, that needs to be considered. The duration of the exercise needs to be considered, as well as the training status and fitness level. The more trained an athlete is, they actually need just a little bit less protein, as we'll see from a table that I've got in this lecture series. So here's that table, the recommendations here. If we go down the list, The first of which is sedentary men and women. So the RDA value, the DRI value is set at 0.8 grams per kilogram per day. So you would take this value here, 0.8, multiply that by your body mass in kilograms, and that becomes the value per day of protein that people who fit into this category should strive for. That value can be pushed all the way up to 1, depending upon the person's needs. Now, as far as athletes are concerned, you can see that going down the list here, depending upon what kind of athlete you are, that's going to dictate how much protein you're going to need. So at the very most, we've got football players and athletes who are in their early training phases consuming about 1.7 grams per kilogram of body mass per day. For female athletes, you would actually take 15% lower of each of these values to come up with the needs for female athletes. So there are some catches to this as far as defining endurance athletes. You'll see that I've got superscripts here, 1 and 2, and that refers to these two variables down at the bottom. So for a moderate intensity endurance athlete, what does that mean? That means that person is exercising 4 to 5 times per week for about 45 to 60 minutes each time, whereas a recreational endurance athlete, they're doing it 4 to 5 times per week for about 30 minutes at less than 55% of their VO2 peak. And this is a table that is out of the Clinical Sports Nutrition book. You'll have more than likely a newer edition of this book, but the table is read the same or in the same manner. Okay, so the big question is, do athletes need to be on amino acid and protein supplements? Are they useful? Are they needed? Well, in general, the answer is going to be no. Most Americans, according to recent data, show that basically the average adult is getting 2 times the RDA value or the DRI value. That's at 0.8 grams per kilogram of body mass. So 2 times, if you figure that, that's over just about or close to 2.0 grams per kilogram of body mass. So that's about what an athlete would need anyhow as a generalization. So with that said, there are certain conditions where protein supplementation, amino acid supplementation can be very, very useful. And so if you have an athlete, particularly that's traveling or that has difficulty in just consuming the overall appropriate amount of kilocalories on a regular basis, they may need to be on a supplement, because if you can't eat enough or the schedule is so limiting and they just don't have enough time to get a good meal, then using a supplement can fill the gaps where that person is not or is deficient. So that's something that we have to consider on an individual basis. So if an athlete has a really rigorous schedule, they're not consuming sufficient amount of kilocalories, then that's when I'm going to recommend, let's do some protein shakes, let's do some protein powder, etc., to fill those gaps, to make sure that we are not putting the athlete at a disadvantage as far as the availability of amino acids for muscle hypertrophy. So with that said, we still don't want to forget about consuming a balanced diet and trying to get as much high quality protein as possible. So just because an athlete's on a protein supplement doesn't mean that we should put them on a fast food chain diet or something like that. We still want to consider high quality protein. We want to consider a balanced diet. So there are always concerns about protein intake, and the problem here with this section is that we don't really know for sure in the long term whether or not these risks are real or appreciable, whether or not they're going to manifest. So that's something that you do want to keep in mind. We don't have any long-term studies, for example, that go out 5 years, 10 years, looking at a lot of these issues. So these are just concerns that scientists have regarding consuming protein in excess. Doesn't mean that this is necessarily going to cause a real or appreciable problem in that particular athlete. So just keep that in mind as you're going through this. So potential risks here. If you're under 2.0 kilograms of body mass per day, that's no more than 35% of total kcals, then you're probably not going to see a lot of side effects. So what we're talking about here are individuals who are consuming more than 2.0 grams per kilogram of body mass per day of protein. So a lot of that protein, most of it is actually going to be deaminated and urinated out. So the concern is that we're placing a heavy load on the kidneys, as we'll talk about. There's always the issue of cost. So if an athlete is relying on supplements and supplement products, then this can add up after a while. And this table just tries to get at that. And although these data are a little bit older, but the point is still the same, that it's costly to be on supplements and these protein powders, etc. So trying to get the same amount of high quality protein from foods, it may be a little bit more work, takes a little bit more planning, but the cost is lower. So if cost is an issue, then this is a consideration that you want to bring up with the athlete. Supplements, depending upon the sources, can be impure. We know that the for the Food and Drug Administration does not police the supplement industry very well unless there's a problem along the way. So it's really the onus or the burden of responsibility for safety is placed upon companies. There have been cases where contaminated L-tryptophan have been on the market, and that leads to a syndrome called eosinophilic myalgia syndrome, which is a painful muscle disorder, and it's irreversible. And so that has happened, and so you want to make sure that the supplements that you're purchasing are coming from reputable sources if you choose to go this route. There's the concern that perhaps some of the impurities might be carcinogenic or mutagenic, and a lot of times for some of the supplements there's no efficacy that's been established, so it hasn't been well researched, and so that's a consideration as well. We want to very, very carefully look at the supplement that we're considering and what are the data, what do the data show us, not just anecdotal information. Poor palatability, that's always a concern. I've tried quite a number of these supplements, these protein supplements, and I can't say that too many of them have a great taste to them. They're certainly consumable. However, that could be a concern for an athlete that you're working with. You may not actually be able to get them to consume that particular supplement, which is where something like a shake works well, where you can add the protein powder and not affect the taste too much. Supplements can be misleading the way they present the numbers on the label, so you got to read very, very carefully. And so they might actually report the amino acid amount in milligrams, which makes things look like they're more than they actually are. So, for example, a half a gram of amino acid, they could report that as 500 milligrams, and you see 500 and think, wow, that's a huge number, that's great. So you really got to pay attention to the units. Or conversely, 7,000 milligrams of turkey, 7 grams of protein. What if we had that on our food labels? It would make it seem like, wow, we're really getting a lot of protein from that turkey. So we need to be careful and read what the units are. A lot of times supplements will have chelators in them to make them more water soluble, and that's included in the overall weight. So we have to look at the amount of grams or milligrams of whatever substance that is in the supplement that we're actually looking at, not the total weight of the package. So we have to be careful about that as well. As I mentioned earlier, renal load is a concern with high protein intake. And again, we don't have long-term studies to show that perhaps consuming, protein at the level of, let's say, 3.0 grams per kilogram of body mass, that is going to cause any renal damage. However, this is just a concern. So one of the concerns is that we will excrete out a lot more calcium, which then may lead to an increased risk for osteoporosis. And what's happening here is that with all the amino acids, of course, we have to deaminate those amino acids, remove that nitrogen group, that amine group, and that's going to actually change the pH a little bit. It's going to make blood a little bit more acidic. So in order to buffer the change in pH, we actually draw calcium from bone and buffer the acid a little bit more with calcium. And so if we are drawing calcium from bone, and let's say the athlete's diet isn't necessarily well equipped with calcium and vitamin D, etc., then that could put that athlete at an increased risk for osteoporosis, theoretically. So we need to be careful with this sort of thing as well. So well-balanced diet, I think, is the key message to come away from in this section here. As far as cardiovascular disease risk, what if the athlete is consuming a lot of meat and dairy products that are high in saturated fat and total fat and perhaps even cholesterol? Are they atherogenic? Are they carcinogenic? Well, again, the answer to this question is really unknown, so this is why it's just a concern at this point. And again, I'd like to bring everybody back to the idea of making sure that we've got a well-balanced diet, making sure that we are introducing good, healthy food into that athlete's diet as much as we can, given the athlete's training schedule as well as traveling schedule. There is the possibility with higher energy-dense foods, like higher fat foods, that perhaps fat gain may occur. So we'll shift the body composition upwards a little bit in favor of fat mass. However, if you think about what an athlete is doing calorically, they're expending a lot of energy, especially these elite athletes. So in my viewpoint, I'm not seeing this as so much of an issue, because they may be having trouble consuming the amount of calories necessary in order to be able to compete and train at their given level. But nonetheless, it's something that we want to be cognizant of. There is the issue of dehydration, simply because of peptide bonds being broken and hydrolysis, and using up water, because hydrolysis is a process where that incorporates water into the splitting of these peptide bonds. And so we could then, because of the urine and the nitrogen and the urea that we're trying to get rid of, accelerate water loss and compounds the problem of needing higher fluid intake. So as we'll discuss a little bit later on with hydration, we'll talk about the guidelines there, which should negate any of these or concerns that we've got about dehydration from high protein intake. As I mentioned, the increased renal load. Again, in the long term, we just don't know how the kidneys are going to be affected by this. In the short term, it doesn't seem like they're affected, but again, the question just remains, what about 5 years, 10 years, 15 years down the road of doing this kind of increased protein intake? We know for sure that patients who have renal or liver disease, that you can accelerate the disease process in those patients. So for those patients, we do want to be concerned with a high renal load, a high liver load as far as protein is concerned. But in healthy people, this doesn't seem to pose any threat, at least in the short term. There's also concern that liver mitochondria morphology might change, so you'll change the way that the cells, the hepatocytes, process amino acids and utilize them for energy as well. So who's at risk for a protein deficiency? Is this ever a problem with the athletic population? Well, there are some populations that we want to be concerned about. Number one on the list here, amenorrheic female runners. If they're consuming a low amount of calories overall, then I'm concerned about protein intake, because the fewer calories that you have to sort of pack in your macronutrients, then the less that you're going to take in protein. And so there's a higher likelihood that you may not be getting all the necessary amino acids. Male wrestlers, simply because of the nature of the making weight and trying to get into these lower weight classes to get some sort of perceived advantage, I'm concerned about that population. If they're not consuming calories because they're afraid of gaining weight, etc., they could be putting themselves at risk for protein deficiency. Gymnasts, overall, both men and women. Let's face it, gymnasts, judges are going to be looking at the aesthetics, the physiques of these individuals, and that's going to take into account, how they get scored and judged. And so if you're really concerned about the aesthetics of how an athlete looks, then you may be running into a problem of lower calorie intake and then lower protein intake. So that is definitely a concern. Same principle here applies to female dancers and even horse jockeys. Because of added weight, the aesthetics of it, the mechanical disadvantage that an athlete might have, these all are concerns. And anytime you're lowering overall calories, you are going to be invariably, unless you're cognizant of it, lowering the amount of protein intake. There's also a concern that it might lead to quote-unquote sports anemia, which we'll discuss a little bit later on in the course. So the practical application of all this material, how are you going to use this information to help your athlete that you're working with? Well, first off is to be realistic about the amount of muscle mass gain or muscle hypertrophy that an athlete can get. From research, we know that we can pack on about 0.25 to 0.5 gram or kilograms, per week of muscle mass. So that's not very much. It's a slow process and it takes time. And that's something that we need to be patient with. So, of course, there are going to be bio-individual variations of this. So genetics are going to play a role, the training history. So the more well-trained an athlete is going to be, the less gain in muscle mass that they're going to be capable of, simply because they're maxing out their genetic potential. But we also want to monitor body composition here to sort of reassure the athlete and showing the numbers like, okay, here we go, body composition, we're increasing muscle mass. So that's a very, very important and useful tool in this process of being real with the athlete and understanding that this is a difficult process, but I want to show you the progress that you've made week to week or every couple of weeks or even month or so, as far as the gains in muscle mass that are attainable by the human body without the use, of course, of things like steroids and growth hormone. We want to always try to follow sound nutrition. And you can use, any kind of food guide that you're familiar with and that you want to use with the athlete to get a balanced diet. I've got here the myplate.gov as an example. However, of course, we can utilize any other food guides there, and the key here is just that it's a food guide. So you're giving the athlete some sort of template for trying to get a well-balanced diet, so that we're getting the appropriate amount of macronutrients, that we're getting all the micronutrients that the athlete needs, and making sure that they have, nutritionally speaking, all of the tools that they need to be able to repair tissue and maintain tissue and develop and improve and optimize performance. So as far as muscle hypertrophy goes, the athlete needs to be training for muscle hypertrophy. So this is hard work. We've got to put in the hard work to get those bigger muscles, to get stronger. So it's not the time to be worried about, losing fat mass. So it's not the time to be thinking about the aesthetics of the athlete. It's the time to be thinking about muscle hypertrophy. So really, this should be reserved for the off season. So we're not really worrying about, fat accumulation and whether or not that's going to hamper my performance because now I'm heavier and, I'm a sprinter and I can't have extra weight on me. This is the time to do it, is during the off season. So we need to train for muscle hypertrophy. It's really important. Eating is very important. So research studies, show that within a 3-hour window, you need to get carbohydrate and protein intake. And of course, we don't want to forget about fat, but particularly carbohydrate and protein, that's going to enhance protein synthesis and get a quicker recovery. There's even some research that shows that there's a 30-minute window for protein intake and carbohydrate intake. So that's really an important consideration, that once the athlete is done training, their next job is to basically go and replenish energy stores, get the macronutrients that they need. Smaller meals may be tolerated more by the gastrointestinal tract. So again, think about an athlete and the amount of kilocalories that they need on a regular basis. Sometimes it's upwards in the 8,000 kilocalorie range. And if you're trying to eat, let's say, a third of those calories all in one sitting, that actually can be quite difficult. So breaking apart the meals into smaller meals even though it may be a little bit more difficult because of schedules and whatnot, may be a better way to go as far as minimizing GI distress. Of course, we want to monitor eating habits. We want to make sure, particularly with the aesthetic sports, that we're looking out for cues of whether or not athletes are going to be at risk for some sort of eating disorder or disordered eating, as we'll talk a little bit later on. So we always want to be monitoring for that and seeing what the athlete is doing as far as diet is concerned. And the last one on the list here is one that can't be glazed over and overemphasized, and that is getting the coach on board as well as the athlete. Sometimes your biggest roadblock will be the coach and not necessarily the athlete. So by developing a good positive rapport with the coach and the athlete, you have a better chance of influencing the decisions that are made as far as dietary concerns go. So that's something you definitely want to work on with the athlete as well as the coach.